Hello everyone, I'm welcome all on Data Phoenix webinar. Today we will speak about different strategy of serving ML models, classic ML models and LLMs. And with us, Ramon Perez. He is developing we can start. Sorry. Also, you can ask all questions using Slando. The link is under the video, and we also will share it on chat on the YouTube. So please use Slando for ask questions, and all your comments you can write on the chat also.
Okay, Dimitri, I am having issues hearing you, but if you are ready to hand it over to me, just give me a thumbs up. And if you can hear me, give me a thumbs up. Okay, all good. So, hello everyone that is in the webinar. I am unable to hear anything right now very well. It's got to be something with my setup, but so long as you can hear me and so long as you can see my screen, then I'm going to continue on. I have on one side the chat and the comments. If at any second you stop hearing me or you stop seeing my screen or anything, please just let me know. I hope there's no difficulties with that. But anyways, let's get started. So my name is Ramon and I work at Seldon. We are a machine learning operations platform and we focus on the last end of the machine learning lifecycle. When I say the last end of the machine learning lifecycle, I mean once you have a trained model, once you have defined the project that you're going to be working on, once you have collected all the data, trained your model, evaluated it, and now you have this artifact, this thing that you want to put into production. You want to have it and you want to make it useful. You want to give some sort of added value. You want to have some sort of value that you're going to extract from, or that you think you're going to extract from this model, and you want to put it in the hands of other users. So a little bit about me. So here at Seldon, I create talks, tutorials, and workshops. I run community events, so please come and join us at our community. We have discussions there, and we talk about all sorts of things related to MLOps. I improve documentation, and I create demo apps with our products. Before Seldon, I was a freelance data professional. I also worked as a product developer, and I also worked as a data science educator and as a research engineer. So I've had quite a broad set of roles throughout my career. I do have a ton of slides today and a ton of content to go over, but I'm going to try and keep it to 45 minutes and leave the last bit for questions. Again, I apologize that I cannot hear anything in case you unmute yourself, but if you put the questions in the chat, then I am more than happy to answer everything I see in the chat. And I see there's a ton of you already putting questions there and commenting, so I'm very glad to see that. All right. So before we get started, I thought it would be important to talk a little bit about the landscape. On the one hand, we have one sphere where we think about machine learning, and then on the other hand, we have another sphere where we think about artificial intelligence. But the reality is that what's the connection in between the two, or what's the convergence? If this was a Venn diagram, where would things fit in or fit under? And here's what we actually think lies at the intersection of machine learning and artificial intelligence today when we think about LLMs. And here I have the automotive industry as an example, just because it's one of the industries where for the past maybe 10, 20 years, we keep hearing that we're going to have these autonomous agents or that are kind of like, or autonomous driving vehicles, and they kind of resemble somewhat AGI because it's an intelligent system that can take us from A to B. And not only that, it understands our preferences and all sorts of other things. But then now we have in the middle kind of like this thing that people think is AI, LLMs. And there's a lot of truth to that to a big extent. But now, why do I tell you this? I'm telling you this because the reality is that there's a lot of decisions that happen at the intersection of these two things. And what we think is revolves around LLMs. There's still a lot of models out there that are for credit decisions, for recommendations, for quality assurance, user experience, autonomous vehicles, personal assistance, damage detection, drug discovery, and energy efficiency. So there's a lot of things that are happening out there that is not necessarily on one side or the other, but it can be categorized as both. And it's not necessarily LLMs. And the way in which companies are combining these two today is by something that we have now centered at, or have now landed at, the acronym of MLOps, or machine learning operations. Not to be confused with the LLMOps that is so prevalent today. So that's a little bit of the landscape. On one hand, you have artificial intelligence. On the other hand, you have machine learning operations. And then in the middle, you have all these important characteristics of machine learning that are taking place today. But also you have the coolest and shiny new things, which are large language models or foundational models. All right. So what exactly are we going to cover today? So we're going to cover the machine learning lifecycle. Then we're going to talk about serving methods, a general approach. Then we're going to go through serving methods, foundational models. And then we're going to go through some examples. So I'm going to give you some code examples, but I am going to keep it at a very high level, so that if you're here to get a broad understanding of the industry itself, then you also get a ton from this session. And if you're here to get a little bit of code as to how things are done, then you also get a lot from this session. And then at the end, I'm going to leave it for some Q&A. So I have about 30 more minutes, and I have a ton of slides, so I'm sure I'm going to fill that up. But please put any questions you might have in the chat. I have it right next to me, and I'll keep an eye on it. All right, so let's start with the machine learning lifecycle. So when we think about the machine learning lifecycle, and we think of the word MLOps, as I mentioned it earlier, which is this whole spectrum of machine learning operations, where that word lands at, MLOps, is in this intersection of machine learning, developer operations, and data engineering. Why those three? Well, there's a lot of reasons, and I have a couple of things to say on those. But on the DevOps side, you kind of need the skills to be able to put these models in front of, in the hands of users, or make them available to other developers, making the logic, your business logic, a reality within your mobile applications or websites or systems. And then on the other hand, you have to have data engineering skills, because machine learning revolves around data. And data is one of the most crucial things that you're going to need in order to extract value from machine learning. And then on the other hand, you're going to need some statistical expertise, and all those three combined come into what we call MLOps today. But if we take it a little bit further, how do we start? Where do we start? So first we have the problem definition, something that we're trying to solve, or a new feature that we're trying to add to our product that depends on automation, on fast decision making. From the problem definition, we're going to get to data engineering, and then we're going to gather the data that we need to train our models. We're going to engineer some features, and then we're going to make that data useful, that data available to our models. Via feature engineering, we're going to craft new things, and then we're going to train a model. Then we're going to do some model evaluation to make sure that works well. Then we're going to do some more. Then we're going to deploy our model. Then we're going to monitor the predictions that our model makes, because we want to make it better in the future whenever it gets to time, whenever it's time to retrain it. Retraining a model is not a matter of do I have to, it's a matter of when. And then lastly, more data gathering. So as you make predictions, your user is going to take action on something, and that action is going to become the real value, not the predicted value. Those two could be one and the same, but they could also be quite different. So that's a little bit about the machine learning spectrum, and then where my company sits at. This is not a sales pitch, by the way, but I want to let you know what I do and maybe why you should listen to me. We focus on this side over here of model evaluation, model deployment, and model monitoring. And then on the other hand, Okay, I thought my slides disappeared for a second. Okay, so then on the other hand, so what about those things that I mentioned? How do we think about them? And if you were to think about a pyramid, where do things land? So, problem definition: badly defined projects can often lead in the machine learning lifecycle. Badly defined projects can often lead to bad outcomes. Data gathering can require a lot of time, can be continuously changing. So there's always some challenges at each one of these stages. And then there can be very complex pipelines where we are using data that is historical from the last time a user signed up to our platform, and also data about their latest activity inside our platform. And now we need to combine data from the past with data from their latest visit, and all of that becomes the input to what is going to be a prediction for the next activity that a user engages in our platform. Then feature engineering features can become very complex in some instances. You can have a feature that depends on time, that depends on activity, and that depends on different characteristics that are demographic itself, or maybe not necessarily demographic, but geographical, and so on. And then at the top, you're going to have the kind of like the money-making object, model training, which as we start using more and more data, starts becoming more and more expensive. So how can we think about it? So in data gathering, when I mentioned can require a lot of time, can be continuously changing. Well, if we combine those two, we also get to the point that there can be a lot of obstacles. Like, for example, how do these two relate to one another? If you think about autonomous vehicles, there can be a lot of obstacles in the street, and this is data that is changing when a model is going to make predictions. If you think about blind spots, that a model is for an autonomous system is changing all the time and is making decisions in real time. So can there be blind spots? Of course. Can there be damaged stoplights? How is a car going to make the next prediction? And all of this that I'm leading you to is I'm telling you why all these pieces of the puzzle are important before I take you to the piece of the puzzle that we're going to talk today about, which is serving. Collision warnings, abrupt weather changes, and so on. So then we come back to the data gathering piece. And then now that we understand like the challenges that can always affect serving, let's go back to the serving piece. When we have a model in production, we usually want to evaluate it. And not only do we want to evaluate it, but we also want to monitor it. We want to make sure that, say, for example, if we work in the financial industry and we are bound to provide reasons for denying a loan application or approving one, well, we want to make sure we can evaluate our model and extract the features that were the most important for a decision. If we are have many models in production, or even just one, we definitely want to monitor them, so that way we want to keep an eye on them, and we want to make sure when the distribution of our data has shifted, that our predictions, if our predictions are still okay, or if they have become, I don't know, the quality has degraded. So one of the questions that you want to ask when you are kind of like scratching the list of these three buckets: can I trust this model? Does it work as intended? Can I extend its usage? Is it compliant with current regulations? And so and when you have it deployed, can I scale it? Can I combine it with different pre and post processing steps? Can I use it as the input, its input as the output for another model? Can I use it as the input for the output of? Can I use the output of one model as the input of another? In monitoring, is my model healthy or drifting away? Has the user behavior changed? If not, if it has not behaved as intended, why is this happening? And so on. So there's a lot of things that we want to make, that we have to keep track in the machine learning space, especially when we have models in production. And you can think about it as a spectrum of what some companies are doing. On one hand, you're going to have your model is going to be deployed somewhere. Nowadays, a lot of models are being deployed on top of different platforms that are using hardware that is hosted in the cloud. And then these platforms are usually built on top of Kubernetes. They don't necessarily have to, but that's a common approach. Even when you are using a Lambda function, that's probably being served somewhere in the cloud. And that's something behind the scenes. Might be on top of Kubernetes. It might not be. But usually we have clients. Clients will be your browser, your computer, an application on your computer, your laptop, your phone, and so on. And then users are going to be, so the server is where the model is deployed. The client is the object that the user is using to send predictions to some sort of model that is hosted somewhere else. And then so that user is going to send in some data. That data is going to come in. We're going to monitor that data. We are going to make a prediction, and then we're going to sort of evaluate what happens with it. Where we operate, I mentioned, is in these three buckets, but I already said that. So we focus on those three, but every single piece of the puzzle is important for the machine learning lifecycle. So now that I told you all of this, let's actually talk about data, machine learning serving strategies. And I put here a general approach because the things that I'm going to discuss apply to not only they apply to some degree to language models, but not necessarily. This is a more generalist approach. Any kind of machine learning model is sort of somewhat game in this one. So before we begin, it's important to know that the process, when we make predictions, that process is called inference. And when we are, when a machine learning model is doing inference, we can do it when we're doing inference when we're using a model to predict something and we're doing inference, we can do it in different ways. We can do batch predictions, we can do online predictions, and we can do streaming. There might be more than that, which is why I put that question mark at the top. But these are three very prevalent ones. So let's talk about each one of the three before we talk about the strategies. So first, batch. What is batch? So imagine I have a very gigantic database with a lot of data. And what I want to predict is that column at the very end of T. That's going to be my target label. And I'm trying to predict that. So I have a model sitting somewhere. And then I have some sort of funnel that is taking all of that data. So I'm going to apply that model to all of that data up here. And I'm going to have a lot of computations. I'm probably going to send that computation once to some sort of maybe a cluster of computers, or maybe just one that is enough or powerful enough to run my computations. After that, I'm going to add those predictions back into another database. And then when a user comes in, say, to watch Netflix, then the predictions, the recommendations are going to be readily available in a database that we can query when the user logs in, and then place those predictions or those rankings right in front of the user. And that is batch in a very straightforward way. There's more ways in which we can discuss what batch prediction is, but I wanted to at least give you an overview of what this is. So then let's go back to the three kinds of methods. And then let's now discuss online prediction. So say you have a person that is filling out a form X, and an application for, say, a loan or something like that. Well, that person is going to fill out, if this is the second time this person is coming to, say, a bank, and it's been, say, 2 years since that person came, we're probably going to have very fresh features, such as the new job, new income, maybe new location where this person lives at, maybe a lot of new things about this person that weren't available in the past. So what's going to happen? We're going to send those new features to a model, and that model, we're going to identify whether we know this person or not. And if we know this person or not, we're going to gather some historical features from when this person came to our bank, maybe 2, 3, 4, 5 years ago, which we probably have that person's gender. We probably have that person's age. We probably have that person's previous location, maybe their marital status, if that hasn't changed, and so on. And then we're going to combine those features, and now we're going to make a prediction after we combine those two, historical and fresh features. So the reason we call it online is because it's readily available to make new predictions on the fly with data coming in, and not necessarily always new data, but data coming in, new data coming in, or new data in combination of historical data, and so on. All right, so that is online prediction. And then, so what about streaming? So streaming is what I'm doing right now. If I had a model translating my every word, or doing speech to text and putting subtitles underneath the screen, then that model will be working on streaming data. So this constant stream of data coming in, and at the same time a constant stream of predictions coming out, is what we call stream. So I had a person here saying, I have a joke, and this person, why did the chicken, and so on. You can probably anticipate what's going to happen next. And then you have a model, probably on AWS or somewhere, anywhere else, in any cloud provider of your choice. And then what comes after is, yo tengo un chiste, por qué la gallina, and so on. And you can imagine what the rest is. But live translation is going to be a kind of streaming, because everything is happening, is very fluid, and it's constant. Okay, so those are the three kinds of methods. There might be more. Now let's talk about the thing that we came here for, the strategies. So in particular, I want to talk to you about 3 deployment strategies for the generalist approach of machine learning. One is embedded models. Another one is model as a service. And the last one is model as data, which I'm only going to touch on very briefly. But still, I'm going to give you a bit of an overview as to what I mean by that. So let's start with embedded models. In embedded models, you're going to have models that are going to be within a website, models that are going to be within a mobile app, for example, and models that are going to be within an edge device. And what does that mean? Let's talk about first within a website. So what are the advantages of why do we want to have, or what are the advantages of having a model within a website? So some of the advantages is simplicity. Integrating the model directly in the website is going to simplify your deployment process. There's no need to manage something separately and have a headache if things go down and things go up and so on. Everything is within one place. The other one is latency. If your model is within your website, chances are it's going to run quite fast, because there's no latency, there's no network, there's no call being sent to another server to get a response and then put it in front of your users. So the latency is going to be reduced. There's ease of maintenance, because if you make if you upgrade your website, or if not upgrade your website, if you change your website in some way, then you can also change your model at the same time, and then you kind of attach the two together. And then resource utilization. So you can share resources between the model and the website. So a lot of times your model might be idle, but because it is hosted within the website in an embedded fashion, then you're most likely to save in resources. You're not going to have to pay for another server containing having your model when you might not be using it at all times, say at 3 a.m. or 4 a.m. In the morning. All right, so those are the advantages. What about the disadvantages of having a model? So at the same time, there's limited scalability. If you have one big website that gets requested by many users across the world, and you have a limit on the resources that you can give to that website, then what's going to happen is that your website is going to crash, or is going to become slower and slower and slower the more people that come in to interact with it. And the same is going to happen to your model. It's going to have less flexibility to be able to talk to people, or to be able to serve its users. The other one is the technology stack dependency. If you're going to have it embedded into a website, then you're going to have to make sure you use the same programming language to read the weights and to serve the model. Then resource utilization, that ties to the scalability. If you have a limit, or if your website doesn't really have that many resources, and your model is being heavily used, heavily pinged to get a prediction, then it is possible that you're going to see slowdowns as well. Updates and maintenance challenges. This is an advantage, but it can also be a disadvantage. You can have a monolith application, but that can make it a little bit challenging to make updates when your model goes haywire. And then increased website load time. I mentioned that. Limited reusability, scalability, and fault isolation. Security concerns. If your model degrades, or if your website gets hacked or whatever, well, they could potentially take the model as well, take the model weights as well, and so on. So difficulty in technology upgrades as well. So those are some of the disadvantages. What about the tools? What can we use today to have a model embedded inside a website? Well, you can have the Transformers.js library. You can have the ONNX runtime, or you can have TensorFlow.js. And notice that I'm focusing here in 3 tools that have JS at the end. ONNX runtime was built by Microsoft and is a model exchange. So you can create a model with scikit-learn, with PyTorch, with TensorFlow, in different scenarios, of course, in different contexts. And then you can change them into another format and reuse that model in a different application. So it has options for edge devices. It has option options for different TensorFlow models. TensorFlow has a different suite of tools, JS, Lite, and regular TensorFlow, and so on. So there's just 3 here, but technically speaking, if you build a website with Python, say with Flask, Fast API, Django, and you have templates in HTML and whatnot, you can still use Python to load your model with a regular application, and then just go on with your day as well and have an embedded system. So when do you want to use this approach? When you're in the prototyping stage, it can serve. When you're in the prototyping stage, it's going to be quite nice to be able to put your model within your website and then not focusing about having to manage different kinds of services at the same time. If your model won't be changing, or you don't need retraining often, then it might be well to have it in your website. If machine learning is not crucial for the functionality of your website, then maybe it is nice to have it there and you don't have to manage another service. When you want to minimize external dependencies, then that's also a good reason if you want to have it within your website. And then lastly, if your website or application is relatively small and simple rather than complex, then you might want to think about having it there. So yeah, if it is crucial that your updates to your monolith happen in a synchronized way, then maybe you also have another reason to have it there. So those are some of the ways in which you can do embedded models. What about within mobile applications? What do we have? So increased privacy. The data is inside the user's phone, most likely. You can do offline inference. So if I go to a remote area and I want to take pictures and I want to classify those pictures, is my model available inside the application? Can I use it offline, or do I have to be connected to the internet in order to be able to use my model? So that's quite a big appeal for having models hosted within applications or mobile apps. Low latency. If the model is within your app and you open the app, then it's going to most likely give you inference, provide you with inference quite fast. Bandwidth savings. You don't have to wait for a request to go over the network and then get the results right back at you. And then energy efficiency as well. Then the last one is compliance with regulatory requirements. And if you don't want to manage and become compliant with a specific regulation, and you always want to have the data inside the users, you can also adopt a strategy which is called federated learning. You can learn the model, you can train the model within the device of the users, and then also do the inference in the device. So what about the disadvantages? Limited computational resources. At the end of the day, a phone, well, nowadays phones have almost as much capacity as laptops 10 years ago. So maybe that there's an asterisk on that one, limited computational resources. Storage constraints, that is true. Sometimes phones tend to have less gigabytes or storage capabilities than laptops or than an iPad or something like that. Battery drain, if you're really hitting that model, say for example, a model is embedded within a game inside your phone, then the battery drain could be higher. Model maintenance and updates are going to happen when you update the app. So similar to the embedded models limitations, training limitations, security concerns, and there could be some security concerns, but there's maybe less than if you have it hosted in its own server. And then capability issues. Also, limited model interactivity. You have a model that does one thing, and if you have too many things if you have a model that does too many things, it becomes a little bit more difficult to monitor the model. So when I mention security concerns, it means that if your model is more often than not being used in an offline setting, then it's going to become much harder to monitor the predictions that it's making, because you're going to have to wait till your user comes back online to send those predictions, or at least to send the analysis back to you. And then initial download size might be quite big. That's another important disadvantage. So then what are the tools that we can use to do embed models within applications. So one is this one. Actually, I put two here that are mostly for training the models on devices, and PySift is one of them. It allows you to do federated learning. So you have the client is going to be the device that you're going to be doing the training on, and then you're going to have something called a strategy. The strategy is going to be how are you going to deal with the weights once they are brought back to your main server. So PySift is one of them. TensorFlow Lite is another one. PyTorch Mobile is another one. Then there's also Core ML for Apple products. There's the Flower framework, which is similar to PySift. It allows you to do the model training on device, and they have they have very, very cool demos in their website. So I highly recommend you check it out. PySift has an amazing community as well, so I definitely recommend that you check them out. TensorFlow JS as well can be used because there are applications that are written in, say, for example, React Native, and that is going to be JavaScript. And so you can use TensorFlow JS as well for edge deployment. Then you're also going to have Transformers that JS and so on. So when to use it when you're doing mobile training. So, or when you are embedding models within a mobile application. So to train new models without needing to see the data, that's a big one, even though it's not necessarily to serve, but you still have the weight inside the device. So technically speaking, you could have some sort of logic that picks up those weights and then makes the model available to the user. When privacy is paramount, when your users will be using the app in offline settings, and I mentioned that already, low latency language translation. That's a pretty cool one. My understanding is that Apple does that and trains small language models based on the way you text. So that way the recommendations that you get are recommendations on the way you speak rather than the way everybody else speaks in the world, which is quite cool. And then, okay. So now that we talked about within mobile device, within edge device, let's talk about within an edge device situation. So what are the advantages? Very low latency. You're going to have a small model inside. For example, here I have a camera. Say, for example, you train a model to recognize all of your relatives, and then you put that model inside. Your camera, and then it recognizes all of your relatives, and then whenever they come, the smart camera or the smart doorbell is going to say, hey, your mom is here at the door, hey, this person is here at the door, and so on. Reduce network dependency. If you're going to have something on edge, it doesn't necessarily mean that it's going to be connected to the internet. As a matter of fact, you can almost kind of count on it not being necessarily connected to the internet unless it's an IoT device. Edge-to-edge communication. It could be, if you've seen smart homes, then you know that there's edge-to-edge communication, and there's some devices are going to be talking to each other and they're going to be connected with one another. Distributed processing, enhanced privacy and data sovereignty. Everything is going to reside within the devices, but that also means that somebody has to physically steal the device from you to be able to access data or even the model itself. Real-time decision-making, improved bandwidth efficiency, autonomous operations, customization for specific edge environments. One of the coolest examples that I've ever seen of edge deployment is this company in Australia is they are putting these devices across farms around Australia to and then what it does is that it sucks in air a few times a day, and then when it sucks in the air, it captures the spores that are in the air, and what it does is that it sends that model. I can't remember if it has the model inside the device, but it does analyze the image, and it detects and it classifies whether the spores have viruses or not. If there's an airborne disease in the air, then they are going to tell the farmer to spray pesticides. And if there's none, then they're going to tell them, don't do it. There's nothing in the air yet. so you're fine. So that way, that saves farmers money on pesticides. Instead of doing it twice a week, 3 times a week, which can cost a lot of money, they can now do it when there's a need, and so on. And this is being done on the edge, which is quite cool. Then let me see. I cannot see the. Okay, can everybody still hear me fine? Can you give me a comment in the chat if you can hear me fine? Or Dimitri, can you give me a thumbs up if you can hear me fine? Okay,
Yeah.
perfect, excellent. All right, so I was here with an edge device. So some of the disadvantages is heterogeneous hardware. You're going to have many different kinds of devices that are going to have different kinds of capabilities. So some of them are going to have very, very little memory, and some of them are going to have even less. Some of them are going to have a little bit more, and so on. And then you still have to put the exact same model into these different devices. Think about, for example, if we go to phones or if we go to doorbells, there's going to be many different doorbells, and you're not going to be able to train the exact same model to recognize my face, my sister's faces, and so on. Maybe you're going to have different models of different sizes in different doorbells in my sister's house, in my house, in my mom's house, and so on. And that's just one example. There's going to be limited processing power as well as memory, resource constraints, ties back to the other two environmental factors. So a doorbell or a smart camera or a smart device inside a house could be affected by a storm if it's outside of the house, or could be affected by a flooding or something like that. There's security challenges because if somebody steals it, they might have access. They might be able to access the model inside that device, or access the data that device collects. Remote management complexity is very difficult. If they're operating offline, it's going to be very difficult to manage them remotely. You're going to have to send someone to service them at some point. Connectivity issues. If they are connected to the internet, it could be that the Wi-Fi chip that it has in it stops working, and you don't know that has happened until after quite a while. Energy efficiency, integration with existing systems, and so on, scalability concerns. So there's going to be a lot of things. And then in terms of the tools that we can use, there's a particular ONNX runtime for Raspberry Pis, which is these devices that you can program for a lot of cool things, to turn on the lights in your house. I used to work at a software engineering academy in Sydney, Australia. And one of my colleagues, one of the lessons that she was teaching was, in one of her lessons, she was teaching how to create how to use a Raspberry Pi that will have inside of it a scanner for the IDs of the students when they will come to the campus. So she programmed this Raspberry Pi and attached it to a little scan code. And then when you will come in, you could pass your ID and it will recognize that it was you, that it wasn't you, and it will log you in. It will say, this person came to class this day, and so on. It was actually quite cool. OpenVINO, specifically for Intel products, hardware, and then TensorFlow.js, which you can use in different applications that might be using JavaScript in some way. So when to use it? For predictive maintenance within IoT devices, smart homes, to make them more efficient. In agriculture, to detect bad spores in the air. That was the example that I mentioned earlier. On device that monitors the health of patients. Security cameras, banks, public spaces, and autonomous vehicles for real-time detection of moving objects, and so on. And then, so lastly, model-as data. What is this? So, or actually, I haven't even talked about model as a service. So there's a couple of things with model as a service. So when you have a service, you have a model inside a dedicated instance. And some of the some of the nice things about it is that you have separation of concerns. So you have dedicated hardware. You can have it as a serverless function, or you can have it as a pipeline. So some of the advantages that the ease of maintenance and updates, enhanced team collaboration, improved testing and debugging, easier scaling horizontally. So if you need more resources, or if you need more instances, so you can scale horizontally and vertically as well. Enhanced development and deployment speed, scalability, flexibility in technology stack. You can pick what you want to use to train the model and serve it, and isolation and fault tolerance. Now, there's a lot of disadvantages, or there can be a lot of disadvantages in this case. Increased complexity. If you have 1,000 models, are you going to have 1,000 teams servicing these models, or you're going to have 1,000 employees, one per model? Or how many, realistically, data scientists can you have servicing a particular model? So there's going to be versioning challenges. If a model goes haywire, how can you go back to the previous one, and so on? Communication overhead, dependency management, data consistency, data transfer overhead, security concerns, and so on. There's a lot of stuff that can happen. But luckily, there's a lot of tools that we can use for that. Hugging Face spaces allow you to create a UI for your model, and also to have an API for your models. There's also Google Cloud Run for creating serverless deployments. AWS Lambda. I've seen the coolest deployments that I've seen is somebody train a linear regression. They take out the weights and put just the weights in plain Python inside a Lambda function. And it's the lightest possible kind of model that you can ever imagine. Bento ML, ML Server, which is the tool that we create here in-house, Rayserve, Replicate has code, and so on. And when to use this? So I think I might have something. I had some stuff here, but there's a lot of instances when you want to use it. And this ties back to the advantages piece of what do you want to have? Do you want to have improved testing, enhanced team collaboration, improved resource utilization, and so on? If your application doesn't depend on the model itself, and it can be retrained in different aspects and in different ways, then have separation of concerns. And that might be one of the reasons why you want to have it. So then we have model as data. And this is a niche category where the models are queried as if they were items in a database. So there was one Predibase started with this concept, if I'm not mistaken. And I think since last year, they have completely switched strategies, and now they're doing LLMs. And I haven't seen anything like the same approach that they had when they were querying a database. And then there's Postgres ML, which is one of the newest one. And for what I've seen, you are querying a model that lives inside a database. So that means that you can have many models in there as well. And then now to the foundation models. So what is a foundation model? Or what are foundation models? So these are large-scale neural networks trained on massive amounts of data. They're models trained on broad, or you can also think about them as models trained on broad data, often in a self-supervised way and at scale that can be adopted to downstream tasks. So what do we mean by that? So we mean more data is for foundational models, more layers. When we realize that we can add just many, many more and then still have a great model, then we just continue on. And then more compute. Those are kind of like the three pieces of the recipe for having for training these massive foundational models. So how do they work? They work in you start first with self-supervised training. You train, say, a model to predict the next word, but this is if we're talking about a specific kind of model. Then you fine-tune that. After that self-supervised training, you might want to fine-tune the generalized model into a domain-specific model, say, for example, finance or healthcare, and so on. And then you might want to do it in a particular task. So instruction. You give the model an instruction, and then it gives you something back. Coding, or question answering, or sentiment analysis, or tagging, and so on. And because I cannot hear anything, let me see if I have any questions or so on. Okay, so I have about 3 more minutes. So let me see if I can finish it then. So what I've been talking about is very much a transformer architecture, which is the most popular nowadays. It's being used for vision, for language, for audio, and so on. So how do we serve them? Well, back in 2016, you will be able to pick and choose the kind of GPU that you want. Now, after 2021, that's kind of like the joke here, that is kind of hard to come by good GPUs because they're very much in such a high demand. So we need GPUs to be able to serve them. So what are the tools that we can use? We can use Truss, Raysurf, BentoML, One Diffusion for diffusion models. We can use Seldon, our tool, Replicate Cog, inference endpoint from Hugging Face. VLLM is a type of server that does continuous batching, and that goes a little bit beyond the scope of the talk, but it's quite interesting that it allows you to use the unused resources in an LLM or in a piece of hardware that is running an LLM in a very efficient way. Deep Speed is one of the best ones out there. It allows you to take many GPUs and it makes them feel like if it were just one GPU. And it uses a very incredible algorithm underneath the hood to be able to do this. So I highly recommend that you learn a little bit more about that one. And then there's NVIDIA's own Triton inference server. Here is the website of banana.dev, the people behind the Potassium framework. And I highly recommend that you check it out because it has a lot of useful information about how inference works for large language models. So I really recommend that. And also in general, if you have a model that is going to scale down to zero, you're going to have to send a payload. And then there's going to be some sort of downtime, which is the cold start, when it's loading in the weights. And then you're going to have the inference period. And then it's going to return a result. And then if it's not used for a while, then it's going to go down to zero again. And there's going to be that cold start problem. But anyways, I highly recommend that you check it out. And now for the last piece, there's a bit of an example. There's a recipe that all these serving tools follow. And you have some sort of module with a super cool class. And then that class is going to be inherited by the recipe. The recipe is you load a model or you load the weights that are being stored somewhere, and then you create your predict function. Underneath that predict function, you might have another one that is going to be, say, pre-process or post-process. But that's kind of like the main recipe of how all of these tools are working behind the scenes to serve your model. You load the weights, you have a predict function. Then you have some package and you do start and then your model.py or something like that. So you pay attention to the load, pay attention to the predict. So then what happens next? You send a request and then you get some sort of, and then after you send a request and you test that is fine, that is working fine, with some package, you're going to send that model to some sort of cloud provider. And then how does that actually work with an actual tool? Here's our tool that we develop in-house, ML Server, an open source inference server. So we have Music Gen, the famous text to music model from Facebook. And we are importing the tokenizer, the processor, and the generator from the Transformers library. We are loading the weights for the auto processor and for Music Gen. And then we have our predict. We take a piece of text that describes the music, and then we pass it, we pre-process it, and then we pass it through our model and generate an output, and it returns back a NumPy array. So we need one more thing, something called model-settings. And then after that, we have ML Server start, and that's how it starts. Then after that, we're going to see the model progressing and starting, and we see that it was loaded successfully. Then we can send a request to that inference endpoint, localhost 8080, model, my model, and so on. And then we can run that Python.test my server and get a result back that is going to look like this. We're going to have an array with data and so on and so on. If we want to create a pipeline, we also do that with one of our tools. You can create a graph, you pass it into your deployment object. And I know I'm hand waving a lot of this stuff because we're running out of time, but I hope this gives you an idea that there's a lot of tools to do different kinds of serving strategies. You have model as a service, you have embedded models, you have model as data, you have pipelines, you have and you have particular different kinds of deployment strategies that you can follow. So I put something funny here, but really that was my presentation. I hope everybody found it useful. Again, I'm sorry that I cannot hear anything. I'm having the biggest difficulty ever with audio and everything else, but I hope all of you found it useful. Dimitri, maybe it will be useful to put the the questions in the from Slido?
Uh, if
Okay,
you,
so I'm going to go
yeah,
through them. And again, Dimitri, I'm very sorry that I cannot hear you. Any advice framework to host 23 billion LLM models embedded on a mobile device? For that, it is very research constrained still. I honestly, I don't know. I have listened to some podcasts about like that have talked about how to deploy LLMs on edge devices, but I have zero experience on how to do so and haven't come across like a good source of information for it that I would recommend. But it's a great question. Starting from open source like OpenAI, this even have it in their names, gaining some user adoption, and then let's go BSL. It is cheating for me. Okay, like OpenAI, I didn't really get the question, but okay. I want to integrate LLMs with contact center real-time calls. How to calculate what environment will be the best in terms of CPU or GPU? I want to integrate LLMs with a contact center real-time calls. That's a great question. So it depends on what kind of like what's the domain of the course. Like if you have a world where you know every question, you have anticipated a good amount of questions that you're going to have, you can calculate, can I put all these questions and possible answers to all of them inside one model? And then if you have a lot of space still available in the model, in the context of the model, then that might be a good size for the model. If you have a lot, then that might be a too large a model to use, and you might be able to afford going with an easy one. What I would recommend is to try a small model first, a small open source model first, and use it with a small amount of calls, see how well it performs, and then compare it to a larger model. Spend a few bucks maybe with the best model out there and see how both of them perform. So that would be my recommendation. As to the device on how to set it up, I would say any provider right now giving you an LLM out of the box with like the recipe and then push it to the cloud or do something with it will work just to test the use case. What approach do you use to estimate LLM implementation in terms of time and cost? Time and cost. I guess it doesn't really come to time. I think to me, okay, personally to me, to answer the question personally, I look for quality. If I first start with quality and then I calculate from the top quality model that I can get, say for example, OpenAI, I say, okay, if I use this LLM to respond to questions, 1,000 questions a day for this particular use case, how much am I spending? And what is the quality of the answers that I'm getting? Then I start testing it with a different model of lower quality, and then I calculate the price of that, and then I compare. So you have to do a bit of experimentation because it's something that everybody's learning how to use. And there's a lot of great resources out there already to estimate cost. But that was a great question. Do you consider BigQuery ML ongoing? With the last category, with Postgres ML, you can query models in it. Yes. So I should have put BigQuery. I didn't put it there because it's not like a specific tool made for that. I'm sorry. It's not like a specific tool from a company. It's like one tool in the suite of tools that Google has. But yes, BigQuery ML. I can't believe I forgot that one. Could you recommend some gold resources for information, digest, webcasts? Okay, so there's 3 that I really recommend, that I really highly recommend. I really enjoy Chip Huyen's posts on LLMs. Eugene Yang. They also have a community in Discord. They both are very prolific writers. And then for podcasts that I highly recommend, I really love listening to Twiml AI and TWIML. And then one more podcast that I really love, or that I have gotten a lot of value from, is Latent Space. So I highly recommend those. Secure document embeddings for LLMs. I think the people at Llama Index are doing some cool stuff with data for LLMs as context for RAG applications. And the people at Quadrant are also doing great work for RAG applications. And yeah, those will be some that I would recommend. But amazing. Thank you very much, everyone, for giving me a bit of your time on a Thursday evening. I really, really appreciate it. Thank you very much, Dimitri, for the invite. It was a pleasure to be with everyone here.
Yeah,
Amazing.
Thank you for
all right.
all
Thank you
that.
very much. I'm sorry that I couldn't hear you, but I'm sure we'll catch up at some
Yeah.
other point. I'm glad that I was able to get the message across and give the presentation.
Yeah. So thank you for all that you was with us, and see you on next webinar.
Okay.
Thank you.
I cannot hear you, but thank you very much, Dimitri. Everyone, have a good evening.